Heavier-than-air flight. In 1895, Lord Kelvin, president of the Royal Society, stated, "Heavier-than-air flying machines are impossible." Simon Newcomb, a distinguished mathematician, published an article in 1903 proving mathematically that powered flight was impossible. Just months later, on December 17, 1903, the Wright brothers achieved sustained powered flight at Kitty Hawk, North Carolina. The scientific consensus against flight was based on careful analysis. Scientists calculated that the power-to-weight ratio needed for flight was insurmountable. Any machine heavy enough to carry an engine would be too heavy to lift off. Mathematicians like Newcomb performed detailed calculations, proving that the energy required exceeded what any engine could produce. The papers were peer-reviewed. The conclusion was accepted as fact. The Wright brothers, two bicycle mechanics from Dayton, Ohio, approached the problem differently. They didn't start with theoretical calculations about what was impossible. They started with practical experiments. They built a wind tunnel and tested hundreds of wing shapes. They developed three-axis control, solving the stability problem that had defeated others. On December 17, 1903, Orville Wright piloted the flyer for 12 seconds, covering 120 feet. By the fourth flight that day, Wilbur flew 852 feet in 59 seconds. Heavier-than-air flight, declared impossible by the scientific establishment, had just happened. Many scientists refused to believe the reports, even when presented with photographs. It wasn't until 1908, when Wilbur flew public demonstrations in France, that the scientific world finally accepted that flight was real. The impossibility of flight wasn't a matter of unknown physics. It was a failure of imagination. The scientists weren't stupid. They were working with accurate physics. But they made assumptions about what solutions were possible, and those assumptions were wrong. The 4-minute mile. For decades, medical experts declared that running a mile in under 4 minutes was physiologically impossible. Doctors stated that the human heart would explode, lungs couldn't process oxygen fast enough, and leg muscles would tear apart. The 4-minute barrier was considered the absolute limit of human capability. Then, on May 6, 1954, Roger Bannister ran a mile in 3:59.4, shattering the barrier. Within 3 years, 16 other runners had also broken 4 minutes. Medical journals published articles explaining why the human body couldn't sustain the required pace. At the speed necessary for a 4-minute mile, oxygen consumption would exceed what the cardiovascular system could deliver. As runners got closer, 4:01, each failure seemed to confirm the experts' conclusions. Roger Bannister, a British medical student and runner, didn't accept this. As someone studying medicine, he understood the physiological arguments but believed they were based on assumptions rather than absolute limits. He thought the barrier was as much psychological as physical. On May 6, 1954, at Oxford, Bannister made his attempt with two teammates as pacemakers. He crossed the finish line in 3:59.4. The impossible had happened. The medical community examined him, expecting heart strain or damage. They found none. Just 46 days later, John Landy broke Bannister's record with 3:58.0. By 1957, 16 runners had broken 4 minutes. The barrier wasn't physiological, it was psychological. Once one person proved it could be done, others immediately did it too. The human body hadn't evolved between 1954 and 1957. What changed was belief. The impossible barrier had been mental, not physical. Landing on the moon. In 1956, British astronomer Royal Richard van der Riet Woolley called space travel utter bilge. Dr. Lee DeForest said in 1957, "To place a man in a multi-stage rocket and project him into the moon is a wild dream, worthy of Jules Verne." Just 12 years later, on July 20, 1969, Neil Armstrong and Buzz Aldrin walked on the lunar surface. The challenges seemed insurmountable. Getting to the moon required enormous amounts of fuel, but carrying more fuel made rockets heavier, requiring even more fuel. Navigation over 240,000 miles seemed impossible. How would astronauts survive radiation? How would they land without crashing? Most scientists believed moon landings, if ever possible, were centuries away. In 1957, the Soviet Union launched Sputnik, demonstrating space travel was possible. In 1961, President Kennedy declared, "This nation should commit itself to achieving the goal, before this decade is out, of landing a man on the moon." The U.S. had only just put Alan Shepard into space for 15 minutes. Landing on the moon within 9 years seemed absurd. NASA began the Apollo program with massive resources. At its peak, it employed over 400,000 people. Engineers tackled each challenge systematically, developing multi-stage rockets, computer guidance systems, the lunar module, and protective spacesuits. On July 16, 1969, Apollo 11 launched. 4 days later, Armstrong piloted the lunar module to the moon's surface with seconds of fuel remaining. Hours later, he descended the ladder. That's one small step for man, one giant leap for mankind. They successfully returned to Earth on July 24th, meeting Kennedy's deadline with 5 months to spare. The moon landing demonstrated that impossible often means we don't know how to do it yet. With sufficient innovation, resources, and determination, the impossible becomes achievable. Breaking the sound barrier. In the 1940s, aeronautical engineers declared that breaking the sound barrier was impossible for manned aircraft. As planes approached the speed of sound, they encountered severe turbulence and loss of control. Several test pilots had died trying. Engineers predicted that shock waves would tear any aircraft apart. Then, on October 14, 1947, Chuck Yeager flew the Bell X-1 to Mach 106, breaking the sound barrier and surviving. The sound barrier was killing pilots. When fighter planes approached sound speed in dives, controls stopped responding and planes shook violently. Sometimes they broke apart. Engineers studied the problem and concluded that transonic flight physics were fundamentally different. Shock waves caused changes in air pressure that exceeded what aircraft structures could withstand. The term sound barrier reflected widespread belief this was an absolute limit. The X-1 was designed differently, with thin wings, rocket engine, and reinforced airframe. Chuck Yeager was selected to fly it. On October 14, 1947, the X-1 was released from a B-29 at 25,000 feet. Yeager ignited the rocket and accelerated. As the X-1 approached Mach 1, Yeager experienced the reported turbulence and control problems. Then something unexpected happened. As it passed Mach 106, the turbulence stopped. Flight became smooth. Controls responded normally. On the ground, observers heard a sonic boom. Yeager had broken the sound barrier and survived. The barrier that engineers declared impossible turned out to be more like a rough patch. The worst turbulence was at transonic speeds, around Mach 1. Once through that transition, supersonic flight was smooth. The impossible barrier was just an engineering challenge that hadn't been solved yet. Splitting the atom for energy. In 1933, Ernest Rutherford, who discovered the atomic nucleus, declared that splitting atoms for energy was moonshine and complete nonsense. Einstein also stated nuclear energy would never be practical. The scientific consensus was that while atoms could theoretically be split, the energy required would always exceed the energy released. Just 9 years later, on December 2, 1942, Enrico Fermi achieved the first controlled nuclear chain reaction, proving nuclear energy was practical. Scientists could split individual atoms by bombarding them with particles, but this required expensive equipment and enormous energy input. Rutherford understood the physics better than almost anyone, and his calculations showed you'd spend far more energy than you'd get back. Einstein agreed. Nuclear energy wasn't economically feasible and probably never would be. What scientists didn't fully understand was chain reactions. In 1938, German scientists discovered nuclear fission. Splitting uranium atoms released neutrons. The crucial insight was that these neutrons could split other uranium atoms. One fission could trigger others in a self-sustaining cascade. You could split one atom and let the process continue. The energy output could far exceed the initial input. Enrico Fermi designed Chicago PL-1, a carefully arranged stack of uranium and graphite. On December 2, 1942, in a squash court under the University of Chicago, Fermi's team began withdrawing control rods. Instruments measured the neutron count, which indicated fission rate. When the final rod reached a critical point, the neutron count stabilized at a high level. The chain reaction was sustaining itself. Fermi let it run for 28 minutes, then stopped it. Nuclear energy, declared impossible by some of the greatest physicists, had just been demonstrated. Within 3 years, nuclear weapons ended World War II. In following decades, nuclear power plants generated electricity from controlled chain reactions, exactly what Rutherford called moonshine. Surviving Niagara Falls. For over 160 years, going over Niagara Falls meant certain death. The falls are 167 feet high, crashing onto rocks and surging currents below. Everyone knew no one could survive. Then, on October 24, 1901, 63-year-old Annie Edson Taylor climbed into a custom wooden barrel, went over the falls, and emerged alive with only minor injuries. Niagara Falls had claimed numerous lives. Boating accidents and suicides all resulted in death. Medical experts explained that the 167-foot impact alone would kill a person, and survivors would drown in churning water or be crushed against rocks. Annie Taylor was a struggling widow and schoolteacher who saw an opportunity for fame. She commissioned a custom barrel, oak and iron with padding inside. Friends said it was suicide. On October 24, 1901, Taylor climbed inside. The barrel was sealed and set adrift. It went over the falls, plunging 167 feet into churning water below. The barrel was caught in turbulent water for several minutes before breaking free. Rescuers reached it and opened the lid, expecting to find her dead. Taylor was alive, with only a small head gash. She'd survived the impossible fall. She became instantly famous, though she died in poverty in 1921. Since Taylor, 15 more people have intentionally gone over. Most survived, though some died. The survival rate is higher than the 0% assumed before Taylor's attempt. Experts weren't wrong that going over unprotected would kill someone, but Taylor changed the parameters by using a protective barrel. This is a common pattern. Impossibilities are often based on specific assumptions. When someone changes the approach, the impossible becomes possible. Climbing Mount Everest. In the early 20th century, climbing Everest was considered physiologically impossible. At 29,032 feet, Everest's summit is in the death zone, where atmospheric pressure is too low for humans to survive. Medical experts declared that above 26,000 feet, humans couldn't get enough oxygen and would die. On May 29, 1953, Edmund Hillary and Tenzing Norgay reached Everest's summit and returned safely. As mountaineers pushed higher on other peaks, they experienced altitude sickness and cognitive impairment. Medical research concluded that above certain altitudes, the human body couldn't function. The death zone was considered the absolute limit. At these altitudes, even breathing pure oxygen wouldn't provide as much as breathing normal air at sea level. Early Everest expeditions in the 1920s seemed to confirm these limits. The 1924 expedition ended when George Mallory and Andrew Irvine disappeared, presumably killed by altitude. Through the 1930s, 1940s, multiple expeditions failed. Medical experts concluded the human body simply couldn't reach 29,000 feet and survive. The 1953 British expedition took a different approach, establishing multiple camps for acclimatization and using supplemental oxygen systems. Hillary and Tenzing were selected for the final summit attempt. On May 29th, they left their highest camp and climbed toward the summit using supplemental oxygen. At 11:30 a.m., they reached the summit. They spent 15 minutes on top, then successfully descended. Medical experts who declared Everest impossible weren't entirely wrong. Unassisted, humans probably can't survive long at Everest's summit. But with supplemental oxygen and proper acclimatization, the summit is achievable. Since 1953, over 6,000 people have summited Everest. What changed wasn't human physiology. It was approach, equipment, and understanding. Transplanting a human heart. In the 1950s and early 1960s, the medical establishment declared heart transplantation impossible. The heart was the center of life, constantly moving, impossible to stop and restart. Even if somehow transplanted, the immune system would reject it. On December 3, 1967, Christian Barnard performed the first successful human heart transplant. The patient, Louis Washkansky, survived for 18 days. Organ transplantation was relatively new. The first successful kidney transplant was in 1954, and only worked because it was between identical twins. Transplanting hearts seemed far more difficult. The heart couldn't be stopped for hours needed to transplant it. The bigger problem was immunological. The immune system attacks transplanted organs. With kidneys, rejection meant dialysis. With the heart, rejection meant death. Most cardiac surgeons believed heart transplantation would remain impossible. Even if the surgery could be perfected, the rejection problem seemed unsolvable. Christian Barnard, a surgeon in Cape Town, disagreed. He believed that with new immunosuppressive drugs and careful technique, it was possible. He practiced the procedure on dogs. On December 3, 1967, a young woman named Denise Darvall was brain dead from a car accident. Her heart was donated. The recipient was Louis Washkansky, dying from end-stage heart disease. Barnard's team performed the surgery over 9 hours. The new heart was successfully connected and began beating in Washkansky's chest. Washkansky survived for 18 days before dying from pneumonia. His immune system was weakened by immunosuppressive drugs. While not perfect, Barnard had proven heart transplantation was possible. Today, heart transplantation is standard, with over 3,500 performed annually in the U.S. One-year survival rates exceed 90%. Continental Drift. In 1912, Alfred Wegener proposed that continents had once been joined and had drifted apart. The geological establishment dismissed this as impossible. Geologists explained that continents were solid rock and couldn't move through solid ocean floors. The American Philosophical Society president called it utter damned rot. For 50 years, continental drift was considered pseudoscience. Then, in the 1960s, evidence from ocean floor mapping proved continents do move, and plate tectonics became accepted science. Wegener noticed that South America and Africa's coastlines looked like puzzle pieces. He found identical fossils on continents now separated by thousands of miles. Rock formations on different continents matched. The simplest explanation was that continents had once been joined in a supercontinent and had drifted apart. Geologists rejected it immediately. How could continents move? They were solid rock. What force could move entire continents thousands of miles? Wegener couldn't explain the mechanism. Without a plausible mechanism, geologists dismissed the theory. The evidence was explained away as coincidence or land bridges. For decades, continental drift was considered impossible. Then in the 1950s, 1960s, ocean floor mapping revealed mid-ocean ridges and showed the ocean floor was much younger than continents. Studies showed the ocean floor was spreading, new crust forming at ridges, pushing older crust away. This explained how continents could move. They were carried on tectonic plates floating on the mantle, with new ocean floor forming between them. By the late 1960s, evidence was overwhelming. Continents did move. The theory of plate tectonics was accepted. The scientific community had declared continental drift impossible for 50 years. They weren't stupid. They were demanding a mechanism, which is proper skepticism. But they were so certain the mechanism couldn't exist that they dismissed strong evidence. When the mechanism was discovered, the impossible theory became fundamental to modern geology. Black holes existing. When Carl Schwarzschild solved Einstein's equations in 1916, he predicted objects so dense that not even light could escape, black holes. Einstein rejected this as mathematically possible, but physically impossible. He published a paper in 1939 arguing such objects couldn't form in nature. The astrophysics community agreed. Black holes were mathematical curiosities, not real. Then, starting in the 1960s, astronomers discovered objects that could only be black holes. In 2019, the Event Horizon Telescope captured the first direct image of a black hole. Schwarzschild's solution showed that if matter was compressed into a small enough radius, space-time would curve so severely that nothing could escape. Einstein found this disturbing. He believed such extreme compression couldn't happen in nature. He argued that before any object could collapse into a black hole, other forces would prevent it. Most physicists agreed. Black holes were impossible. In the late 1960s, astronomers discovered intense X-ray sources. Some, like Cygnus X1, showed characteristics that could only be explained by black holes, enormous mass in tiny space. Evidence accumulated through the 1970s, 1980s. By the 1990s, scientific consensus had shifted. Black holes weren't just possible, they were common. Still, all evidence was indirect until 2019, when the Event Horizon Telescope captured the first direct image of a black hole, the shadow of the supermassive black hole at M87 center, silhouetted against glowing material. Einstein had declared black holes impossible. For decades, physics agreed. They were wrong. Black holes weren't just possible. They're common throughout the universe, fundamental to understanding galaxies. Cloning a mammal. Throughout the 1980s, 1990s, the scientific consensus was that cloning a mammal from an adult cell was impossible. As cells differentiate into specialized types, they permanently lose the ability to become other cell types. An adult cell couldn't be reprogrammed to become an entire organism. Then, on July 5, 1996, Dolly the sheep was born at the Roslin Institute, cloned from an adult mammary cell. The impossibility was based on solid biology. During development, cells divide and specialize: neurons, muscle cells, skin cells. This differentiation was thought to be one way and irreversible. Once specialized, cells lost the ability to become other types. You couldn't clone from adult cells because they had already committed to being specific cell types. Numerous scientists attempted adult cell cloning and failed. In 1984, embryologist Dave Orsolter stated, "The cloning of mammals by simple nuclear transfer is biologically impossible." Ian Wilmot's team at Roslin Institute took a different approach. They used somatic cell nuclear transfer, taking an adult cell's nucleus and inserting it into an egg cell with its nucleus removed. The key innovation was starving the adult cell first, forcing it into a dormant state. This, combined with the egg's environment, reprogrammed the DNA. The egg developed into an embryo, implanted into a surrogate mother sheep. On July 5, 1996, Dolly was born, a clone of the 6-year-old donor ewe. The announcement shocked the scientific world. Many didn't believe it. Once authenticity was confirmed, the declaration that adult cell cloning was impossible was overturned. Since Dolly, many mammals have been cloned from adult cells. The technique declared biologically impossible is now, while difficult, definitely possible. Running a sub-2-hour marathon. For decades, a sub-2-hour marathon was considered physiologically impossible. Sports scientists calculated that running 26.2 miles at the required pace, 4:34 per mile, would demand oxygen consumption beyond human physiological limits. Projections suggested sub-2 hours wouldn't be broken until 2075, if ever. Then, on October 12, 2019, Eliud Kipchoge ran a marathon in 1:59:40, breaking the barrier. The marathon world record had been improving gradually, standing at 2:02:57 by 2014. Sports scientists analyzed the physiology, the sustained aerobic capacity, oxygen consumption, and energy expenditure required, and concluded sub-2 hours represented an extreme limit. Eliud Kipchoge, a Kenyan runner, became obsessed with breaking 2 hours. In 2017, Nike organized Breaking 2 in Monza. Kipchoge ran 2:25, agonizingly close. 2 years later, the Ineos 159 Challenge was organized in Vienna specifically to break 2 hours. This was an optimized time trial, laser-guided pacemakers, perfectly flat course, ideal weather, and carefully timed nutrition. On October 12, 2019, Kipchoge started in Vienna. His pacemakers maintained exact pace. He ran with metronomic consistency. He crossed the finish in 1:59:42, the first human to run a marathon under 2 hours. The achievement was controversial because of pacemakers and controlled conditions. It didn't count as an official record. But Kipchoge had proven sub-2 hours was physiologically possible. Sports scientists had to reconsider. The physiology hadn't changed. What changed was optimization. Ideal conditions, perfect pacing, advanced shoe technology, optimal nutrition. Bumblebees Flying. An urban legend claims scientists calculated bumblebees shouldn't be able to fly. While partly myth, it's based on real 1934 calculations by Antoine Magnan, who applied fixed-wing aircraft aerodynamics to insects and concluded bee flight shouldn't work. He was wrong because he used the wrong model, but for years, scientists genuinely didn't understand how bees flew. In 1934, Magnan applied airplane wing calculations to bumblebees and found their wings were too small relative to body weight to generate sufficient lift. He published this, noting it was puzzling that bees could fly when calculations suggested they couldn't. The problem was, Magnan used the wrong model. Airplane wings generate lift through steady airflow over fixed wings. Insects don't fly like that. Bees' wings flap, rotate, and create vortices. The aerodynamics are completely different. Applying airplane equations to bees was like explaining helicopter flight with airplane equations. Through the 1930s, 1960s, scientists genuinely didn't understand insect flight well. In the 1990s, 2000s, researchers using high-speed cameras and computational fluid dynamics finally explained it. Bees' wings create complex vortices and generate lift through dynamic stalling. The aerodynamics are entirely consistent with physics. The story has become a popular metaphor. Don't let people tell you something is impossible just because they don't understand how it can be done. The bumblebee doesn't care about calculations. It flies anyway. Quantum tunneling. In classical physics, particles can't pass through barriers they lack the energy to overcome. Like a ball can't roll over a hill if it doesn't have enough energy to reach the top. This was considered absolute. Then quantum mechanics revealed quantum tunneling. Particles can tunnel through barriers they classically couldn't cross. This seemed to violate energy conservation and was initially considered impossible. But experiments confirmed it happens, and it's now fundamental to understanding atomic physics, nuclear fusion in stars, and how electronic devices like tunnel diodes work. Classical physics was clear. A particle with insufficient energy to surmount a barrier would be reflected. It couldn't magically appear on the other side. The energy barrier was absolute. Quantum mechanics revealed something strange. At quantum scales, particles don't have definite positions. They exist as probability waves. When a particle encounters a barrier, there's a small but non-zero probability the particle exists on the other side of the barrier. The particle can tunnel through. When this was first predicted, many physicists considered it impossible. It seemed to violate energy conservation. How could a particle cross a barrier without having the energy? But experiments confirmed tunneling happens. The particle doesn't actually go over the barrier or break through it. Quantum mechanics describes reality probabilistically. There's a probability of finding the particle on either side. Quantum tunneling is now understood as fundamental to nature. It's why the sun shines. Hydrogen nuclei tunnel through electrical repulsion barriers to fuse. It's essential for understanding radioactive decay and modern electronics. What seemed impossible by classical physics is routine in quantum mechanics. Spaceflight. In 1920, the New York Times mocked rocket pioneer Robert Goddard, stating, "Professor Goddard does not know the relation of action to reaction. He seems to lack the knowledge ladled out daily in high schools." The Times said rockets couldn't work in space because there was no air to push against. For decades, this view was common. Spaceflight was impossible. Of course, the Times was completely wrong. Rockets work by Newton's third law and work better in vacuum. After the Apollo 11 moon landing, the Times published a correction. It is now definitely established that a rocket can function in a vacuum. The Times regrets the error. The belief that rockets needed air was surprisingly common. The reasoning seemed intuitive. Engines push against something. Car wheels push against roads. Propellers push against air. Therefore, rockets must push against air. In vacuum, rockets would be useless. This was wrong. Rockets don't push against external medium. They work by Newton's third law. For every action, there's an equal opposite reaction. When rocket fuel burns, hot gas is expelled at high speed. The action of expelling gas creates reaction, force pushing the rocket forward. Actually, rockets work better in vacuum than atmosphere because there's no drag. Robert Goddard proposed in 1920 that rockets could reach the moon. The Times ridiculed him. For decades, Goddard was mocked. He continued research privately, developing liquid fuel rockets. During W-Wind, Germany developed the V-2 rocket. After the war, space programs developed. In 1957, the Soviets launched Sputnik. In 1961, Gagarin became the first human in space. In 1969, Apollo 11 landed on the moon. After the moon landing, the Times published their correction, admitting the error. They'd been absolutely certain spaceflight was impossible. They were completely wrong. They'd misunderstood basic physics. The impossible spaceflight became routine. These 15 achievements were all declared impossible by experts. These weren't uneducated opinions. They were respected scientists, engineers, and doctors using the best available knowledge. They performed calculations, cited physics principles, and explained logically why these couldn't be done. They were certain, and they were wrong. What these stories reveal is that impossible usually means we don't know how yet. It requires technology we don't have. It contradicts our current understanding, or I can't imagine how. True impossibility, violations of fundamental physical laws, is rare. Most things declared impossible are just very difficult, or require approaches that haven't been discovered yet. The pattern is consistent. Experts declare something impossible based on current knowledge. Then someone tries a different approach. Technology advances, or understanding deepens, and the impossible becomes possible. The Wright brothers didn't accept that flight was impossible. They experimented until they found a way. Bannister didn't accept 4 minutes was absolute. He trained to break it. NASA didn't accept the moon was unreachable. They developed the technology. These achievements also reveal how psychological barriers masquerade as physical ones. The 4-minute mile and 2-hour marathon weren't truly physiological limits. They were psychological barriers that, once broken by one person, were quickly broken by many. The sound barrier wasn't actually a barrier. It was a rough transition that seemed impassable until someone pushed through. There's a lesson about skepticism and humility. Healthy skepticism is valuable, but declaring something impossible requires extreme confidence in current understanding. History repeatedly shows our understanding is incomplete. Physics of the early 1900s didn't include quantum mechanics or relativity. Biology didn't understand DNA. What seemed impossible then became routine later. When experts declare something impossible today, they're basing it on 2024's knowledge. But 2024's knowledge is incomplete, just as 1900's was. Some things declared impossible today will turn out to be merely difficult. Some will require technologies we haven't invented. Some will require understanding we haven't achieved. This doesn't mean everything is possible. Some things genuinely violate physical laws. But history suggests caution about declaring things impossible, especially when based on we can't imagine how, rather than this violates fundamental laws. The 15 achievements in this video were all impossible until someone did them. They teach us that human ingenuity, determination, and creativity can overcome barriers that seem absolute. They teach us that expert consensus can be wrong. They teach us that impossible is often temporary, waiting for the person who refuses to accept it and finds a way anyway. The next time someone tells you something is impossible, remember, people said the Wright brothers couldn't fly, Bannister couldn't break 4 minutes, Hillary couldn't climb Everest, and NASA couldn't reach the moon. They were all wrong. The impossible happens all the time. It just requires someone who doesn't believe in impossible.